Okay, now we're going to look at an example in which you can practice using your basic understanding of organic reaction mechanisms to analyze a reaction you may not be familiar with. All right, so the question here is write the mechanism for the proton transfer for these two compounds. So the two compounds are sodium amide and methanol. So the first thing you do when you get a problem like this is you want to rewrite the reaction. There are a couple reasons to do that. You want to show the bonds and the lone pairs that might be involved in the reaction, and you don't know what they are exactly because you haven't completed your analysis. But it's helpful to see what bonds are there, what lone pairs are there, so that it can help you with the analysis. The second thing is it helps you identify any ionic compounds so that you can identify spectator ions. Spectator ions are ions that, as they sound, just watch what's going on. They don't participate, so they can be ignored. So anytime you see something that's an ionic compound, often one of those ions is just there to be a counterion to make the total thing neutral. And so we want to do that. So looking at this molecule, we see this reaction, we see sodium amide. So sodium amide, sodium is in the first column of the periodic table. Since it's in the first column, it's really electropositive. It often forms, almost always forms, ionic compounds. So we can be reasonably comfortable writing the sodium part as an ion, +1. All right, and so if the sodium is +1, that means the NH2, or the amide, is a -1. So let's see what that looks like. So if we write the NH2, two hydrogens bonded to the nitrogen, for that molecule to be negatively charged, the nitrogen having a formal negative charge of -1, means there would be 6 electrons around it. So that means there'd have to be 2 lone pairs. So sodium +1, amide -1 looks like that. All right, so looking at the other reactant, CH3OH, methanol, that compound, we sort of say, okay, we remember that hydrocarbons aren't functional groups, they're less reactive, so we're not going to draw out all the bonds to carbon and hydrogen, so we'll leave those in condensed formula, just for now. And then we see, okay, there's a bond to oxygen and a bond to hydrogen, and then there's 2 lone pairs on oxygen if it's going to be a neutral oxygen atom. So these are our reactants, and we can identify the sodium as a spectator ion, so we just say, okay, I don't care about that anymore and pay no more attention to it. Now we turn to our analysis of the reactants and decide what could possibly react with what. And the first thing to do is to identify both electron-rich atoms and electron-poor atoms. So we'll start with electron-rich, which we're going to symbolize with red charges, or delta pluses, or full plus, electron-rich, delta minuses and minuses. And then we're going to look at electron-poor atoms, which we're going to symbolize by blue with delta pluses and pluses. So in these two molecules, the electron-rich atoms are the electronegative atoms, right? They're the ones pulling electron density towards themselves, so they're electron-rich. More important than the electron-rich, the electronegativity aspect is a charge aspect. So in this reactant, the amide, the nitrogen is negatively charged. So we would say that this is a very electron-rich atom. So I'm going to re-emphasize that by putting that in red. So there's a full -1 charge on that nitrogen. So that's very electron-rich. Oxygen, on the other hand, is electron-rich because it's more electronegative than the atoms it's bonded to. So we're going to say it's partially negative charge. Put a delta minus. All right, so delta minus means that we're showing that electrons have been pulled towards it, but not so much that there is a full -1 charge. So that's the electron-rich atoms. Let's look at the electron-poor atoms, and those are symbolized by blue, or pluses. All right, and so anything attached to an electronegative element is electron-poor. So if we look at the most electron-poor atoms, we're going to go to the more electron-poor molecule, which is the neutral molecule, and we're going to say what's attached to the oxygen. Well, the hydrogen is directly attached, so there's an electron-poor, and the carbon is directly attached. That's also electron-poor. So there's 2 electron-poor atoms on methanol. And then this other molecule in the amide, relative to nitrogen, yes, the hydrogens are electron poor, but the whole thing is electron rich because of that negative charge. So we'll just symbolize those sort of conflicting things by making this, yes, electron poor, but only a little bit, so little delta pluses show the little bit of delta plus. So then when you look at the overall set of reactants, we can predict that the most electron-rich thing is probably going to form a bond with the most electron-poor atom. So in this case, the nitrogen's lone pair is going to form a new bond with, well, either the proton or the carbon, but remember that this is a proton transfer reaction. So since that's the case, we know that the nitrogen lone pair is going to make a bond with that hydrogen. So I'm going to use curved arrows with green to show the electron flow. So we'll take a lone pair on nitrogen, doesn't matter which one, show it making a new bond with hydrogen. In order for it to make a new bond with hydrogen, if we don't want to violate the duet rule for hydrogen, we have to break a bond, right? So make a bond to hydrogen, we'll have to break a bond, so the only bond we can break is this to oxygen. So that means the bond pair is now going to become a lone pair on oxygen. So let's draw what the product of these reactants would look like. So here's the reaction arrow, and we say, okay, so that nitrogen had bonds to hydrogen that we haven't changed, so I leave them alone. There's a lone pair we haven't touched, so I leave that alone. So this lone pair has now become a bond pair to hydrogen. Alright, now let's look and see if there's any formal charges. Nitrogen should have 5 electrons around it to be neutral. It does, so it's no formal charge. Perfect. What about the other product? Well, the H3C has not changed, so we just leave that alone. The oxygen's 2 lone pairs haven't changed, but now one of the bond pairs became a lone pair, so we'll go ahead and draw that. And so now we take a look at that product and we say, all right, is there a formal charge? This oxygen has 7 electrons when it should have 6 to be neutral, so that's a negative formal charge. And so now we have our 2 products. We have methoxide and ammonia. And so that's how you would analyze a reaction where you aren't necessarily sure which proton is being transferred to which atom. And this is the kind of analysis that will be useful to you in future reactions, not just proton transfer reactions.